So in the previous lecture, you saw that there are 15 system exceptions and 240 interrupts or external exceptions. And now in this lecture, let's explore different system exceptions. So remember that in ARM Cortex-M X processor, there is room for 15 system exceptions. All right. So there is a room for 15 system exceptions. Exception number 1 is always reset exception. All right. Or you can also call it as reset system exception. And remember that only 9 implemented system exceptions. There is a room for 15 system exceptions, but only 9 are implemented in the hardware and 6 are reserved for future implementations. All right. And the exception number 16 is called as IRQ1 or interrupt 1. All right. So now let's go to the generic user guide and let's explore. So in the generic user guide of the ARM Cortex-M processor, in the section exception model, you will find one subsection, exception types. Here it is. These are the different system exceptions. Now, if you just browse through this document, here you will find one nice table, and first 15 are the system exceptions, different system exceptions. So what are those system exceptions? Reset, NMI, hard fault, memory manage, bus fault, usage fault, SVC call or SV call, PendSV, and SysTick. All right, so these are system exceptions, and from exception number 16 onwards, these are interrupts or IRQs. All right. Now, and if you can count here, only 9 are implemented. All right. So in between you see reserved here. Great. Now you can understand more about these exceptions by just reading through this document over here. Now let's go on by one. So what is reset? So reset is a system exception which is triggered or invoked on power on reset or warm reset. So the power up reset is nothing but that is one reset circuitry in your hardware board. So that means when you give supply to your board, that reset circuitry will trigger the reset exception, or it will assert the reset signal of the microcontroller, which will end up causing this exception inside the processor. Warm reset means you can also trigger this exception by pressing a button, a reset button on the board. Okay, so that's what we call as warm reset. All right, so that is you do the reset by pressing a button. Now we have already explored the reset sequence of the processor, isn't it? So in which we saw that whenever you reset a processor, a reset handler will be triggered, isn't it? So the processor will start executing the reset handler, and from there control reaches to the main function of the application, isn't it? So when reset is asserted, the operation of the processor stops potentially at any point in an instruction, and when reset is deasserted, execution starts from the address provided by the reset entry in the vector table. So the meaning of this sentence is when reset is deasserted, execution starts from the reset handler. All right, so you have to write a reset handler, and from there the execution starts. All right, and execution restarts as privileged execution in thread mode. So remember, reset handler execution is always in thread mode, but it is privileged because the processor by default will always start in privileged access mode with thread mode, isn't it? So non-maskable interrupt. So this is not actually a system exception. So this is a exception triggered by the peripheral. All right. So or you can also trigger this exception by software. Okay, it's possible. In fact, any exception you can trigger by software. Okay, And let's read this paragraph here. A non-maskable interrupt can be signaled by a peripheral or triggered by a software. So this is the highest priority exception other than reset. So reset has got the highest priority and it is permanently enabled and has fixed priority of -2, and NMIs cannot be disabled or masked. Alright, so this is very important and you have already experimented with this, isn't it? Like the fault mask or pre-mask registers, they cannot mask out the NMI interrupt. So it's a non-maskable interrupt. So now next is hard fault. So now we have already seen the triggering of hard fault exception, right? For example, when we were doing the experiment of T-bit, right? So we saw that hard fault triggered whenever we try to execute any instruction by keeping T-bit as 0, isn't it? So remember that hard fault is an exception that occurs because of an error during exception processing. Let's say you are already in some exception handler, and if you commit any illegal instruction or any illegal code access or any illegal instruction execution, then at that time the hard fault exception will be triggered. Okay, and it can also be triggered because of an exception cannot be managed by any other exception mechanism. Take an example of your T-bit experiment. In the T-bit experiment, you try to execute an instruction by keeping T-bit is equal to 0. So that should actually trigger the usage fault exception of the ARM Cortex-M processor. But at that time, you didn't enable the usage fault exception, isn't it? So that's why the exception will be escalated and it will trigger the hard fault. All right. If there are no exception handlers enabled in order to handle a particular exception, then by default hard fault will be triggered. All right. So and you need not to enable hard fault exception. It will be enabled by default in the processor. All right. So this we will experiment in the next lecture. Now hard faults have fixed priority of -1. Okay, and meaning they have higher priority than any exception with configurable priority. So this also we'll see later. And next is memory manage fault. So this is an exception that occurs because of memory protection related fault. All right, so this is to do with memories. If your code tries to access some protected memory, then memory management or memory manage fault exception will be triggered. And this happens when you enable the memory protection unit of the processor to guard some of the memories. For example, consider a real-time operating system or embedded OS in which the kernel code can restrict user applications or user tasks to touch some memories. Okay, so if your task tries to read or write into that memory location, memmanage exception will be triggered, and memory management exception will be triggered, and the RTOS can forcefully end that task or it can take any other action. So in that cases, memory manage exception can be used. And next one is bus fault exception. So this we will encounter rarely. So bus fault exception usually happens because of the bus errors, and this we encounter very rarely in our program. And next one is usage fault. So usage fault can be triggered, okay, for any of these reasons, like undefined instruction. So this we have already seen, isn't it? So in our T-bit experiment, we try to execute instruction by keeping T-bit is equal to 0. So when T-bit is equal to 0, the processor thinks that that instruction belongs to ARM instruction set. So that's actually an undefined instruction for the ARM Cortex-M processor. So if you try to execute any instruction by keeping T-bit is equal to 0, that is considered as undefined instruction for the processor. So that's why processor should trigger the usage fault exception. All right. So now the usage fault can also be triggered during unaligned data access. Okay, we will see this in the next lecture. okay, how we can trigger how processor triggers the illegal unaligned access and invalid state or instruction execution, an error on exception return, etc. Okay, and these are very important. Okay, I will discuss more about this in the later lectures. The following can cause a usage fault when the core is configured to report them. That means you can configure the processor code to report these activities. So report means how? By triggering the usage fault exception. So we will do some experiment. We will try to divide by 0, and we will also try to do unaligned data access, and we'll see whether it generates usage fault or not. All right, now there are other 3 system exceptions like svcall, pendsv, and sysdig. So these are very important system exceptions. They are there to help the embedded operating system design or real-time operating system design. All right, so for example, sysdig. A sysdig exception is an exception the system timer generates when it reaches 0. So sysdig timer is a peripheral of the ARM Cortex-M processor. So it is one of the peripheral. All right, so the sysdig timer you find inside the processor, remember. So all ARM Cortex-M processor, they come with internal sysdig timer, and you can use that timer in order to generate interrupts for a fixed time interval. All right, so you can use it just like you are any other timer peripheral of the microcontroller. And whenever that counter value of the timer reaches 0, the sysdig timer will generate an exception. And in OS environment, the processor can use this exception as system tick. For example, in your real-time operating system or embedded OS, you can use this sysdig feature of the ARM Cortex-M processor in order to implement the kernel ticking. Okay, so in order to perform context switching or in order to implement blocking call, etc. So you can use this as a kernel tick timer. All right, great. So now these are another 2 important system exceptions given by the ARM Cortex-M processor to efficiently design the operating system. So svcall stands for supervisory or supervisor call. So this is an exception that is triggered by the svc instruction. So in an OS environment, applications can use svc instruction to access OS kernel functions and device drivers. So in an embedded OS scenario, what happens? You have kernel code which is privileged, and you will be having a couple of tasks which are unprivileged. So whenever the unprivileged task or code blocks, if they want to take any, if they want to touch any device drivers or any peripherals, then they cannot directly go and touch the restricted resources, right? So because peripherals in those cases will be considered as restricted resources. For example, memory is also a restricted resource. So in that case, application can request for service from the kernel, and for that purpose the svc instruction is used. So the application has to execute the svc instruction along with the service number. All right, so all svc instructions will be executed with service number, and that execution of svc instruction will cause svc exception, and the mode of the processor will be changed to handler mode, and the svc handler will run in the kernel mode, and in that svc number will be decoded, and respective services will be provided to the application. So it is to implement that system call interface layer. Okay, so this svc instruction is used, and we will do some exercise to understand this. And the next one is pendsv, and this is also a OS friendly exception given in the ARM Cortex-M processor, and this is used for context switching in the operating system like FreeRTOS or OpenRTOS. All right, so if you check the source code of FreeRTOS, then you will come to know that they use PendSV exception in order to implement the context switching. And don't worry, we will explore more about PendSV in the later part of the course. All right, so here in this lecture I just wanted to show you the supported system exceptions. All right, so there are 9 supported system exceptions out of 15, and after 15 system exceptions, IRQs start. So 16th exception number is IRQ 1. Okay, so that's an interrupt. All right, great. So now in the next lecture we will address more information related to this, and we will explore some of the other fields of this table like priority, vector addresses. Okay, great. So I'll see you in the next lecture.